this computer. Okay, so we are talking today about 7.1, integration by parts. And maybe just a little bit of prelude, into chapter 7. Chapter 7 is all about different integration techniques. I've told you guys kind of time and time again throughout chapters 5 and 6 that, our integration skills are weak right now. All we really know is U sub. We can do U sub, and certainly some, elementary antiderivatives, but we don't know many techniques for finding antiderivatives. And chapter 7 is when we become strong. We learn lots of different techniques for finding antiderivatives. And so the first one that we're going to be talking about is integration by parts. And so maybe to start, just a quick reminder of what integration by parts says and kind of a quick skim over the pre-class videos that you should have watched before coming today. With integration by parts, this is integrating some, again, complicated function here. Oops, I forgot because I restarted my iPad. I need to tell it that I have an Apple Pencil again by plugging this thing in. There we go. So yes, you have some complicated thing. And in order to integrate this, or one way that you can integrate this is by kind of swapping things around, right? Maybe you don't like the setup where you have f and g prime, or really we're going to use a lot of u's and v's and stuff like this. So primarily we're going to be picking a u and a dv, and then we can calculate out v, and of course u we already have chosen. And then later on we'll need, of course, du as well. And maybe this thing is easier. If it's not easier, right, don't use integration by parts. Don't use this method. But if it is easier, and we'll see a variety of cases where it indeed is easier, then this is one technique that you can use in order to evaluate out antiderivatives. And by the way, just from the proof, this really just comes from the product rule for derivatives. Just kind of rearrange things and integrate on both sides. And that's exactly where integration by parts comes from. And of course, this is all set up for indefinite integrals. You can also do it for definite integrals. You can just plug in bounds and all that sort of stuff. And so here's some examples of things that you can do. For instance, like x times cosine x, or really anytime you have a power of x times a trig function or a hyperbolic trig function. Things like a power of x next to an exponential. This is also a classic integration by parts style problem. And then you get some ones that are maybe less standard, right? When we were originally talking in chapter 6, 6.2, 6.3, 6.4, all that sort of stuff, we learned how to take the derivative of the natural log, but we couldn't integrate it. Turns out you needed integration by parts for this. So now that we have integration by parts, we can integrate the natural log. And likewise, when we talked about, in 6.6 or so, when we were talking about inverse trig functions, right? We could take the derivative of inverse trig functions, but we couldn't integrate them. Turns out whenever you want to integrate an inverse trig function, you need to use integration by parts. And so now we can do a few more things. So there's a few like ad hoc, types of questions that now we can integrate that we couldn't do before. And this is the most difficult example. Maybe when you were watching the video, you said, geesh, this is a tough one. This is one where kind of it wraps around on itself. And then we end up with an expression that has what we were trying to solve for, both on the left and the right-hand side of the equation. And then we can rearrange and divide, and we can get a final answer. So that's kind of a unique one. We'll do one of these today as well, just so we can get a little bit more practice with this. Fadi asks, is this on exam 1? No, the chapter 7 stuff is not on exam 1. So this will not be on tomorrow's exam. It'd be a little bit cruel to, have it today and then test it immediately on the exam tomorrow. It's just too fast, right? You got to have time to do the homeworks and all that sort of stuff. Okay, so I guess before we get into the problems for today, let's see if folks have any questions out there. So Yuan, what's going on in the Q&A?
Someone is asking, will they able to take the practice exam tomorrow morning?
Yes, I believe the practice exam closes or is like due or something like this at like 5 o'clock. And that's just so that students don't get confused between the practice exam and the actual exam. Before we used to do that, we had situations where students said, I accidentally took the practice exam rather than the actual exam. And then that's a sad way to use your dropped exam, And so you really want to make sure that you're clicking those buttons to take the real exam. And so that's why we kind of close it at a certain point, just to make sure that everyone's taken the real deal. The practice exam is on D2L under the exams tab, just an FYI. Maybe one more question or so?
What would you say the level of the difficulty is of the exam, I guess?
I don't see. This is just, you're setting me up to fail, Yuan.
Yeah, that's
no, whoever asked this question, they're setting me up to fail because, no matter what I say, right, I'm wrong. Because for some people, the exam won't be so bad at all, right? And for some people, the exam will be very difficult. And so I think no matter what answer I give here, I will be wrong. And so, yeah, I guess from my perspective, it's an easy exam. I can do all the questions. But yeah, no, I don't think that's what you necessarily want to hear. I'm hoping that we wrote a reasonable exam. I hope that we chose questions, and I've looked over this and everything that are in line with what you saw in the Webwork homeworks and the quizzes and things like this. We're not trying to trick you and whatnot. So I hope we wrote a reasonable exam. Whether it's easy or difficult really will depend on your skill level, I guess, or I don't know, or how familiar you are with those particular questions. Let's take one question from a student who has a raised hand. Anito, you're up.
I have a question with the pre-notes.
Yes.
It was for 7.1.4.
7.1.4.
Yeah, so you had to integrate by parts twice, basically. And so for the first U, you chose x squared as your thing. For the second U, why'd you choose x instead of x squared again? Because never mind, it's in the second part of the integral. I was looking at the beginning.
Yeah. Okay, great. I'm glad that you saw that. And we will be hitting this hard again I have another problem that's similar to this in our class notes. That's important, kind of what you choose for your U and your DV and everything. So I'll be covering that again. And when I cover it here in class, if it's still not, or if you have another question that comes up, please let me know. Okay.
All right, for sure. Thanks.
Awesome. All right. So let's then talk about our particular questions for today. And I'd like to tell you a little bit about a good rule of thumb. And if you Google search how to do integration by parts and whatnot. And I didn't know about this when I was taking calculus. No one ever told me about this, but I think it's quite nice, is that there's a good order of operations that works 90% plus of the time. And so it goes, it's called Lyot. I don't know how you exactly pronounce it. This is how I'm going to pronounce it, Lyot. But yeah, so L is for logarithms. I is for inverse trig functions. A is for algebraic. T is for regular old trig functions. And E is for exponentials. Oops, I already have the E. And if things are closer to this end of the spectrum, you're much more likely to choose them for your U. So for your U, or the thing that you're going to take the derivative of. If things are closer to this end of the spectrum, exponentials, trig functions, stuff like this is what you're much more likely to set as your DV. So this is what you're likely to integrate. And we'll see that in many of the situations that we come across in today's class that this follows pretty much exactly. And a comment from someone saying that in some places they see that these things are switched. And that's fine. I would say it's very unlikely to see both of those in the exact same problem. And so it shouldn't come up a whole lot. But if you like iLate or whatever, then that's certainly fine as well. So let's go ahead and try to apply this. And again, kind of as you watch the pre-class videos and everything, you'll see that kind of we follow this format here. And so for these integration by parts problems, I guess, first of all, luckily, for the upcoming exam, integration by parts will not be on it. And so again, kind of when you solve the problems on the exam, our kind of most powerful technique of integration is U substitution. But if you sit and you try U substitution on this for an hour, for 2 hours, for a day, for 5 days, whatever, right? You'll just spin your wheels for a long time, and sadly, no U substitution will work. So it's not that, we could use U substitution and we're just making it more complicated for the fun of it, right? It's that no matter what U substitution you try, it just doesn't work. And so we need something else in order to solve a problem like this. And so that's where integration by parts comes in. And just kind of maybe before I get into the explanation here, the only one that's maybe a little bit questionable is what are algebraic functions, right? So logarithms, I hope we all know what logarithms are, the natural log, log base 2, stuff like this. Inverse trig functions, very clear. Trig functions, exponentials, I hope that these are all clear. Algebraic are things that maybe we don't, usually give names to. These are things like, again, x or x squared. It's any of our polynomials. Also things like the roots. So square root of x, stuff like this. Even if you have like the cube root of x plus 1, this would be an algebraic function. So any of these would be algebraics. So just as kind of an FYI before we get into this. So we can see in our case, we have an algebraic and we have a trig function, right? So the algebraic is the x here, and the trig function, of course, is the cosine. And so when I go to use integration by parts on this, well, we can see that the algebraic, this is the closest thing that we have on the u side of things. So this is going to be what we set u equal to. And on the bottom side of things, right, we have dv, well, trig functions, right? So cosine of 2x, dx. This is what we're going to set our dv to be. So now, again, we've set this up so that we can use integration by parts on this. According to integration by parts, if you want to integrate u dv, which again, we've chosen our u, we've chosen our dv, that this is equal to uv minus the integral of v du. So you can see that we need to calculate out a few things, right? For instance, I don't know what du is. I need to use my substitution here in order to calculate that out. And likewise, I know what dv is, but I don't know what v is here. So we have to spend a little bit of time calculating these things. So let me cheat using technology. I apologize for anyone who doesn't have enough room here, but I think it's nice to keep these things all together. So when I take the derivative of u to get du, well, of course, the derivative of x is 1 dx. So there we go. That's how we can swap out our u's and our x's here. And then, of course, if I have dv, I'm going to need to integrate this in order to get to v. Now, this here technically is a small u substitution. And I'm hoping that we've had a lot of practice with u substitution so that you get kind of quite quick at this. You don't need to spend a lot of time formally doing the u substitutions for things like this. So I'm going to go ahead and write down, I know the integral of cosine is sine. And then I'm off by a little bit, right? If I was to take the derivative, this wouldn't get me back to exactly where I started. So the question is, what do I need? What should I include in addition to the sine here in order so that it gets me back exactly to where I started? And yeah, a lot of this coming in chat, and I also see in the Q&A. Excellent. So yeah, I need to include this 1/2. Now this takes into account the chain rule, right? Because when I take the derivative of sine, I do get cosine. Leave the inside alone, right? The 2x stays alone. And then you need to multiply by the derivative of the inside. And the derivative of the inside is 2. So you need something to cancel it out, right? I don't see a 2 up here. It's got to cancel out somehow. How does a 2 cancel out? Well, a 1/2 does it perfectly. So, okay, we need to include the 1/2. Again, this is formally a small u substitution. And if you're not comfortable with this yet, do the small u substitution and make sure you get this right. All right, so now we have all of the pieces. Let's go ahead and set this up. So again, uv, so uv minus the integral of v du. So the integral of v du, and du is just the same thing as dx. And so again, we need to kind of look at this. I'm meant to have closed parentheses here. We need to look at this and say, right, is this integral easier than what I started with? Because if it's not easier than what I started with, then I shouldn't do this integration by parts. I should try something else. Maybe this is a u sub problem or something like that. But in this case, right, well, we could pull out this 1/2, and then we're just integrating sine of 2x. And yeah, I think that this is a fairly straightforward u substitution, just like when we integrated cosine of 2x. And so, yes, I think that we can do this. Yes, it seems simpler, so I'm happy with the direction that we're headed, and we should see this one through. So let's go ahead and integrate sine. When we integrate sine, we're going to get negative cosine. So this becomes negative cosine of 2x. And just like before, right, if I just left it like this, I'd be wrong, right? Because I need this extra 1/2 to cancel out, right? If I was to take the derivative of this to get back to where we started, right, that 2x, this chain rule, needs something to cancel out with it. And so that's why the 1/2's there. Again, this is a small u substitution, and I hope that you get to a point, hopefully by the quiz that will cover this next Tuesday, and if not, by exam 2, which will cover this, that you're doing these u substitutions, these small ones, quite quickly, and you don't need to spend a lot of time on them. Okay, let's see. Whenever we integrate, we can have a plus c, and let's go ahead and spend one line to clean this up. X over 2 sine of 2x. We have two negatives here, so these are going to make a positive. So we're going to add, and we have a 1/2 and a 1/2. That makes a 4th cosine of 2x plus constant of integration. So this right here would be my final answer. And I guess, you know, if you were ever taking a quiz or an exam, something where you had to do this problem and you were paranoid that you did something wrong, of course, the way to check this is to take the derivative of your answer and hopefully see that you get back to where you started. Now, this is only if you have extra time, obviously, right? But this certainly a fine way to go for like the learning sets and all that sort of stuff. All right, let's see what kind of questions are out there. Yuan, what are you hearing about on the Q&A?
Someone's asking about the 1/2.
The 1/2, yeah. So let me do the, I'll do the u substitution formally here one time, okay? And then from the rest of the class, I'm going to try to skip that. Otherwise, we're going to spend a lot of time on u substitution, and we're not going to be able to talk about integration by parts much at all. So when you want to integrate this, technically you want to make u equal to 2x, the inside function. So du is equal to 2 dx. So dx is equal to 1/2 of du. So then when you go ahead and you substitute this in, this is going to be the integral of sine of u. And instead of dx, we're going to write 1/2 du. And so you can see right here, this is where the 1/2 comes from. It's the swap from x to du in this viewpoint. When you integrate sine, you get negative cosine. We can swap back in. Instead of u, we can put 2x. And again, you can see this 1/2 hanging out here. I don't really have enough room, but technically there's supposed to be a plus c here, plus c. So yes, that's where the 1/2 comes from. It's this small u substitution, switching out our u's for our x's and then back. All right, why don't we go ahead and try this next one here. This next one, notice that, we have a hyperbolic sign. That's a little bit interesting, right? I don't have anything, in my rule here about the hyperbolics. But I'd like to give you guys maybe 90 seconds or so. Try this one out, see what you would do here, and then we'll spoil the surprise together. So I see there's quite a few Q&A questions and whatnot. I'll help out with those for just a minute. But try this one out on your own. Pretend it was a quiz or an exam question, not for exam 1, but for exam 2. Try to see how far you can get. All right. Well, the correct way to handle this is just like the previous problem. Even though you have a hyperbolic function here, still we're going to let u be equal to our algebraic thing, our x. And then dv is going to be equal to this thing that, again, resembles a trig function very much. So hopefully you guessed this anyway. Let's calculate our du, which is, of course, just 1 dx. And when we integrate this, the integral of hyperbolic sine is hyperbolic cosine. And just like before, when magically, you know, those 1/2s appeared, because again, the chain rule or a small u substitution, likewise here, you're going to have a 1/3. And of course, be paranoid, double check. If you take the derivative of this, you should get back to where you started. So now that we have the setup, we can say that this is going to be equal to, and this is going to be uv. So uv minus the integral of v du. And du is dx. So very much like the last one here. Let's see, we can take out this 1/3. And when we integrate hyperbolic cosine, we just get hyperbolic sine. And then you yell at me, what did I do wrong? Yep, I see it coming up in the Q&A. Excellent work. We need an extra 1/3, right? There's technically a small u sub going on here, just like before, right? If you take the derivative of this, you don't get back to where you started. And so, yes, you need an extra 1/3. And let's see, if you were to multiply these together, well, 3 times 3 is 9. So, right, this is the final answer you can do is 1/9. All right, there we are. Let's do one more here pretty fast, and then we'll open it up for questions. Here's one where we have x squared e to the negative 5x. So again, kind of if we go back here, this one does really fit into this model well. We have our algebraic stuff, x squared, and we have our exponentials. So you can kind of see the thing that's closest to the u is the algebraic stuff, the x squared in this case, and then the dv, the exponentials. So let's go ahead and set this up. I'm going to try u is equal to x squared, and dv is equal to e to the negative 5x dx. Again, kind of this is a classic integration by parts sort of deal, a polynomial next to an exponential e here. And so when we calculate out the derivative, we're going to have 2x dx. We have v is equal to e to the negative 5x. And again, when you integrate e, you get itself. But technically, there's a small u substitution, you know, similar to the ones above here. And so you need to multiply by 1 over negative 5, or negative 1/5. This is Clove. Clove has come to help me out. Hello, Clove. And this is Nutmeg. Nutmeg has decided she will help out as well. Thank you, Clove. Thank you, Nutmeg. All right. So this is the antiderivative of e to the negative 5x. Now let's go ahead and plug these things in. So we have uv. I'm going to rearrange this a little bit. I like my constants out in front. Minus the integral of v du. So let's see, v and du. Du is a little bit more complicated this time. It's 2x dx. And so let's spend a line to simplify down. So this is going to be negative x squared over 5, e to the negative 5x. We have minus a negative, so that's going to be plus. We can factor out or kind of remove these constants out into the front. So we have a 2 on top and a 5 on bottom. And then we're going to have x times e to the negative 5x. And again, the question we always ask ourselves is this simpler than it was before? Is this a good path to take, right? Because if it's not simpler, then maybe we should try something else. And so when we look here, well, before we had an x squared, and now we have an x. So even though I can't solve this as it sits, right, it is simpler than it was before. And I have high hopes. Actually, if I make, if I do another integration by parts, I know that the derivative of x is 1. And kind of this is why we choose our algebraic stuff quite often to be the things that we're taking the derivative of, is because if you take enough derivatives, eventually they simplify down very nicely, right? The derivative of the derivative of x is 1, and then that is essentially gone, and you only have to worry about our dv stuff. Or in this case, if you start at x squared, maybe it's not a surprise that you really need to apply integration by parts twice. So we are going to apply integration by parts twice. I'm going to go ahead and kind of pull this off and make it a small subproblem here. Well, I don't know about small subproblem. We'll say medium subproblem here. So I'm going to try to find this answer. And then once I have that, I'll plug it in up here. So let's see, if I was solving this as its own problem, well, again, I see an algebraic and I see an exponential. So I'm going to let u be equal to the algebraic stuff, and I'm going to let dv be equal to the exponential stuff. When I take the derivative, we get du is equal to dx. When I take the integral, I get e to the negative 5x times a negative 1/5. Again, there's a small u substitution going on here in order to get that negative 1/5. So when I go to evaluate this, this is going to be equal to uv, so x, negative 1/5, e to the negative 5x, minus the integral of v du. So v and du is just dx. We can do a little bit of simplifying. Minus a negative is going to be plus. We can bring out this 1/5, and the integral of e to the negative 5x is just itself. Well, almost. We need to also include in this negative 1/5, again, from a small u substitution. And so the answer to this problem right here is going to be negative x over 5 e to the negative 5x minus 1/25, right? Those two 5s on bottom multiplied together become 25, and then e to the negative 5x. Technically plus a constant of integration. Oh, I didn't know I got comments like that. Let's go ahead and copy this and move this up. Like I said, once we have this answer here, we can just input it here. So let's make this our final answer, negative x squared over 5 e to the negative 5x plus 2/5 times this integral, which notice that that 2/5 has to be distributed to both pieces, right? It's 2/5 times the entire answer there. So one common mistake that I see is folks only take the 2/5 and multiply it by the first bit, and they forget about the second bit, plus a constant of integration. And so this right here will be our final answer. Of course, you can simplify things down a little bit if you'd like. For instance, each one of these terms has an e to the negative 5x, so you could factor this out. I'm going to have to turn off my notifications somehow. But yes, that's how you would solve this problem. Well, I see a few folks with raised hands, so why don't we call on these guys first here, and then we'll see what's going on in the Q&A. Let's see, Jack, you're up.
Hi, Professor. Can you hear me okay?
Yeah, sure can.
I just had a question regarding the example 12.
Yes.
If we look at the first line there, where we've got x multiplied by 1 over 3 hyperbolic cosine of 3x. I wasn't sure why that wasn't. Oh, you know what? Never mind. I see that. Okay. And then just the other, back to the one that we were on, that constant, or the constant c. In that case, we don't need to include that in parentheses just because it's a constant anyways, and it would be a constant multiplied by a constant.
Exactly, right? So even if you wanted to include it inside of the parentheses there, then you would have 2/5 times a constant. And since we don't know what that constant is anyway, right, we would, thank you, cats, we would still have another constant, right? And maybe you want to call that d or something like this, or c tilde or whatnot. But yes, it would just be some constant. We still don't know what it is. Any old constant works.
All right, thank you very much.
Yeah, of course. All right, what's going on in the Q&A, Yuan?
Someone's asking, would they be marked down if they use integration by parts by tomorrow's exam?
If you use integration by parts on tomorrow's exam, something has gone wrong. I would say that, like I mentioned before, that integration by parts solves different types of problems than U substitution. So the types of problems that we're choosing for the exam, of course, don't have integration by parts on them. Many of them are probably solved with U substitution. And so they're meant to be solved with U substitution. If you try integration by parts, it's something that, again, you could end up spinning your wheels for a long time. And you won't end up getting the right answer because it's not meant to be done with integration by parts. There are some problems out there that can only be solved with U substitution and not integration by parts. And there are other problems out there that can only be solved by integration by parts and not with U substitution. And so I would be wary about mixing them up too much. Sorry, I have to get my lucky spray bottle here. This cat is going for my computer cords at the back of my computer. And that's really the only thing that they're not allowed to bite on and pull on and all that sort of stuff. So they've backed off for the time being. All right. I thought I saw one more hand. Let's call. Oh, nope, it's down now. So, okay, let's do another problem.
I want to ask another question about the exam.
All right, go for it.
Yeah, is the exam are going to be curved?
No individual assessment has been curved for a long time. So it's unlikely that the exam itself would be curved because it really depends on what the grade distribution look like at the end of the semester. We have a lot of leniencies built into the course, right? We have a dropped exam, we have lots of dropped quizzes, we have 15% being added here and there and all that sort of stuff. And so at least last semester, this well accounted for many of the hardships, I guess, with being an online class and all that's going on out there in the world and everything. So we have high hopes that it will also, do its job, I guess, this semester. If that turns out not to be the case, we would probably curve the overall course grades, not so much a particular assignment. So that's typically how it goes anyway. All right, one question here, and then we should do another problem. Arian, you're up.
Hey, can you hear me?
Yeah, sure can.
All right, so this is more of a logistical question. Last semester in Math 132, we had extra points on the exam. So if you lost a few points, another question would just add on those points. Do we have something of the sort in this exam, or is it just like all of the marks are just 100?
I don't know the answer to that question. See, if you look at some of like the old in-person exams, the same time that those extra points were added to the exam coincided with when we added these more challenging problems, right? There was an entire page or 14 points on the exam that were, I think at least at one point it was 14 points, that were dedicated to more challenging problems on the exam. Since we don't have those for our online class and our online exams, I think that we've moved back down to just, regular old 100 points because we've taken away these challenging questions. I'm not 100% sure on the answer to that. So I need to maybe double check with someone to see if that's the case or not, but that's my best guess. Okay.
All right. And would getting a cat help me in the exam by any chance?
Cats always help. Yes. They're very lucky, especially for math. Have it nearby. Shut it in the room with you. Okay. All right. Excellent. Let's go ahead and do another problem. Like I mentioned in the video, I think this is maybe the most difficult type right here of integration by parts. When you have a trig function or a hyperbolic function and an exponential. So, right, we have cosine and we have e to the negative 2x. This is going to be one of these that ends up wrapping around on itself. Again, the strategy does work here. So if we go back here, we see that we have an exponential and we have a trig function, two things that kind of live quite low on the list. We're going to go ahead and let u be our trig functions, and we're going to let e, our exponentials, be our the things that we're integrating, our dv's. So u is going to be equal to our trig function. And then dv is going to be equal to our exponentials. When we go ahead and we calculate out du and v, we get something like this. Again, you'll see lots and lots of times here we're doing many u substitutions over and over again, right? So when we integrate e to the negative 2x, right, there's this negative 1/2 that pops out. Again, this is from the mini u substitution that we did. When you go ahead and you simplify this down, someone mentioned the dx. Thank you very much. When we take the derivative of du, you should get a dx. Absolutely. Now, when we go ahead and use our integration by parts rule, right, we're going to have uv, so cosine of x times v, e to the negative 2x times negative 1/2, minus the integral of v du. V du, and du has this negative sine of x dx. Let's take a line to simplify this down before we look and see what exactly we have. So let's see, I have a negative 1/2 out here. I have a cosine, and I have an e to the negative 2x. That's in the first bit. In the second bit, right, it looks like I have a total of 3 negative signs. So it'd be minus, plus, minus. So yes, we have 3 negative signs. So this is going to be minus. We can go ahead and bring out this 1/2 here. And then we're going to have the integral of sine times e to the negative 2x. And I think we got it all there. So now we look at this integral and say, you know, is this simpler? Is this making progress or whatnot? And especially in this case, it's questionable. And this is why it's the most difficult type of problem that we have, I would say, for integration by parts, right? Because this doesn't look any better than this. And so you really have to know that, you know, something good happens if you proceed. And if you do one more step, it does wrap around on itself, and we are able to solve this problem. So let's go ahead. And again, I'm going to make kind of a quick side problem here where I'm just trying to solve this. So I'm going to do, maybe move down a little bit farther this time. The integral of sine of x times e to the negative 2x dx. And I'm going to do yet another integration by parts on this, right? I start fresh. I look at this and I see we have a trig function and we have an exponential. So according to our integration by parts technique, we'll let u be equal to our trig function. We're going to let dv be equal to our exponential. When I take the derivative, I'm going to get cosine of x dx. And when I take the integral, I get, well, a copy of itself. It's an exponential after all. And then from our u substitution, we're going to have this little negative 1/2. And sorry, I forgot the dx right here, technically. So now when I use the integration by parts here, we're going to have uv. So u is sine of x, and v is this e to the negative 2x times negative 1/2, minus the integral of v du. So v, that's the e to the negative 2x times negative 1/2, and du is going to be my cosine of x dx. Let's take one line to simplify and see what we have. So let's see, we have a negative 1/2 sine of x e to the negative 2x. Let's see, it looks like we only have 2 negative signs this time. So negative and negative becomes positive. We can factor out this 1/2, and we're going to have the integral of e to the negative 2x cosine of x dx. And let me just see, I think, yeah, this is how I want to write that. So this right here is equal to my integral. And again, when you see this, you can see that this problem right here is the exact problem that we were tasked with solving, right? Look at this. It's the exact same function that we have up here. So a funny thing happens. We're going to be able to solve for this now using algebra. So let me show you again how this works exactly. Again, I'm going to go ahead and copy this. This up here, this here, copy. And I'm going to input it in for my answer, right? I just figured out what the integral of sine of x times e to the negative 2x. So this is what I'm inputting it in for. So let's go ahead. Again, we have negative 1/2 cosine of x e to the negative 2x minus 1/2. And then here is where we put our answer. Paste, right? Cheat using a little bit of technology here. So whatever you had for your answer, right, this is where you paste it. And again, I have a string of equal signs, right? We need to remember what's on the other side of this equal sign, right? We have the integral of e to the negative 2x cosine of x dx. So I have the exact same thing here as I have here. This is kind of like, if I had, a is equal to, 5 plus 2a or something like this. And I told you to solve for a, right? You would try to accumulate all of the a's on one side of the equation, right? Maybe bring them over here. You would have negative a is equal to 5, and then maybe divide by something in order to get the final answer, right? So we want to accumulate this thing that we're interested in solving for, right? Our a in this case is a lot more complicated. It's this integral thing, right? But we want to accumulate them all on one side, and then we maybe have to divide by something. So that's going to be our strategy. So there's a few lines of simplification, a few rearrangement steps here that we need to do, and then we'll have the answer. So let's go ahead and maybe first, I can see this negative 1/2 has to be multiplied by all of this. So I'm going to go ahead and distribute that to kind of both pieces. All right, Kat. No chords for you. No chords. All right. So let's go ahead and distribute that negative 1/2. Isn't this fun, right? This is why usually they have all of their food in a litter box and stuff like this in a bathroom back there. That's why they're usually in there for class time. So again, distributing the negative 1/2, this is going to become plus 1/4 sine of x e to the negative 2x. And then when I distribute the negative 1/2 to the second bit, we're going to have negative 1/4, and then this integral that we're interested in solving for. So again, this is my a. It's a rather complicated, ugly looking a, but again, you treat it as the thing that you want to solve for. It is the unknown. And so I want to add, right? We have 1 over here, and I'm going to add 1/4 of them, right? So if I bring that over to the other sides, well, 1 plus 1/4, that's going to be 5/4. I'm going to have 5/4 of these things that I'm interested in solving for. And what's left on the right-hand side? Well, we have the negative 1/2 cosine of x e to the negative 2x plus 1/4 sine of x e to the negative 2x. Yes. And so lastly, if I want to solve, not just for 5/4 of them, right? But if I want to solve exclusively, what is this thing? Well, I need to get rid of the 5/4. And of course, the way that we're going to get rid of the 5/4, according to our algebra days, right, is that we're going to multiply by the reciprocal. We're going to multiply by 4/5. 4/5. And we're going to multiply this on both sides. By the way, so if I was entering this into WebWork, I would probably do a few things here. I'm happy with this, I suppose. But I would factor out, I see both of these pieces have e to the negative 2x. So I'd probably factor that out. Bring that. And then I'd be left with negative 1/2 cosine x here and plus 1/4 sine x for my second term. And of course, anytime we take an antiderivative, right, we should have this constant of integration. Of course, this simplifies a little bit more. Some of you are probably eyeing the fact that I have a 4 up here and some 4 and a 2 down here. So yes, it does simplify a little bit more, but this is where I'm going to leave it. We've spent enough time on this problem, at least here in my perspective of it. So again, these are the most complicated types of integration by parts. They're ones where they wrap around on themselves, right? In the process of doing integration by parts, part of our answer was exactly what we were trying to solve for originally. And so we can get the solution by just rearranging and doing a little bit of algebra. So it's kind of a funny thing, but it works, right? If you take the derivative of this, you'll see that this is indeed an antiderivative. You get back to where you started. And so I invite you maybe once in your life to take the derivative of this and really see that, yes, you do get back to where you started. So yes, this is a legitimate technique for finding antiderivatives. All right. Well, with that, I'm sure there are some questions. So Yuan, what's going on in the Q&A?
Where did you get the 5/4?
The 5/4. So over here, we had the integral that we were trying to solve. And remember the coefficient, if the coefficient's not showing, right, the coefficient is 1, right? So there was one of these things that we were trying to solve for. And then over on this side, we have -1/4 of, again, that exact same integral. So I guess a better example here is that if I had a on this side and I had, -1/4 a on this side, then what would you do, right? You would add this -1/4 a onto both sides, and this would be giving you 5/4 a, right? You have your full a, or 4/4, and you're adding 1 more fourth to that, right? And so that's where the 5/4 comes from. And then you can go ahead and rearrange a little bit. And now let me update my answer. My answer would be 4, right? Because I need to multiply by this 4/5. And so things cancel a little bit. So yeah, rearrange, combine like terms. Even though your like terms are very interesting and weird like terms, it all works out. Excellent. Any other questions on the Q&A?
Yeah, would there be a bonus questions on the exam?
I already answered that. So
Okay.
go back and replay my words from about, I don't know, 15 minutes ago. All right. Well, let's do another one here, right? So my final example is one, like I mentioned, that is a little bit more ad hoc, right? But again, this will follow the rules, right? In this case, we have x and natural log of x. We already saw in the video how you could integrate the natural log of x, and this works out perfectly fine. This also will work well with integration by parts. So again, if you remember the layout, there we go. In this case, we have a logarithm and an algebraic. So two things that are fairly high up here. Remember, near the top, this is things that you want to take derivatives of. And near the bottom, this is stuff that you would want to integrate, right? So you'd want to set to your dv because you'll integrate it to find v. So we'll go ahead and give this one a go. U is going to be equal to, again, our log. We had a lot of situations in today's class where we set u equal to x. So this is a little bit different, right? So we're setting u equal to the natural log. And dv is going to be equal to our algebraic thing, x. When I take the derivative, well, the derivative of natural log is 1 over x dx. And the integral of x is 1/2 x squared. Sorry, there should be a dx right here. And so when we use our integration by parts here, we get uv minus the integral of v du. And now you can see why this works out so well, right? We have a little bit of cancellation here. X squared here, a single x on bottom. And so this just becomes, and I'll rearrange this a little bit, maybe have my x's out front and then my natural log. And this is going to be 1/2 and the integral of x dx. And again, we ask ourselves, are we making progress? Does this seem to be heading in a good direction? Is this easier to integrate than what I started with? And I hope we have a resounding yes, right? That this certainly is easier than what we started with. Very nice integral indeed. And so when we integrate this, we're just going to have this 1/2 x squared. And we can do one line of simplification. Plus a constant of integration. And that right there is going to be our final result. And of course, if you had any extra time on a quiz and an exam, if you wanted to verify that this is indeed a correct antiderivative, you could take the derivative of it and see that you get back to exactly where you started. All right. Well, that's going to be, well, it's all the problems for today. We got through them all. I can't believe it, right? It's 2:40. Ended perfectly on time here. As always, we'll stick around for a little bit and answer any kind of questions on this stuff. Again, this will not be on the exam tomorrow. And so I completely understand if you kind of purge this from your memory temporarily and whatnot. Study for the exam, make sure you do well on that, and then come and hit this chapter 7 stuff hard, starting on Friday. All right, guys. So we'll start taking some questions and whatnot. Good luck on the exam and everything. And I will see you guys Friday.